Hello guys, welcome back to my channel. Please remember to like and subscribe. Now today we're going to explore the properties of the determinant of matrices. And because it's pretty easy to work with a 2 by 2 matrix, we're going to explore the properties using the 2 by 2 matrix. So here we have a 2 by 2 matrix. And of course we have a shortcut for finding the determinant. Most persons use the product of the leading diagonal, which is that minus the product of the non-leading diagonal. So the determinant of A here would be A11 times A22 minus A12 times A21. That's the determinant of A. The first property we want to look at is what happens with the determinant of A transpose. So the first thing I'm going to do is to transpose the matrix. Now when we transpose the matrix, the row becomes the column and the column becomes the row. So we could start here. If I were to transpose row 1, I would have A11 here, A12 there, and A21 here, and A22 there. Now, let us see what happens when we find the determinant of A transpose. Determinant of A transpose, applying the same shortcut rule, which is the product of the leading diagonal. And now the leading diagonal here is going to be A11, as you can see here, times A22 minus A21 times A12. Now, of course, even though we have A21 and A12, the thing is commutative, so we can actually switch it. So right away, we can conclude that the determinant of A transpose, which is a transpose of A, is actually equal to the determinant of A. That's the first property we want to explore. For my next property, we're going to look at what happens when we interchange two rows. So here I'm saying that row 1 goes to row 2 and row 2 goes to row 1. So the matrix is going to become, so let me write this properly. So we're going to end up with the determinant of A21, A22, A11, A12. We apply the shortcut again. We take the product of the leading diagonal and we subtract the product of the non-leading diagonal. So I'm going to have A21, A12 minus A22, A11. Now, of course, when you multiply two constants, multiplication is commutative. So if I wanted, I could switch the A21 and the A12. So I could say A12, A21 minus A11, A22. Now, how do I compare this to the previous determinant? If we were to factor out the minus sign, I would end up with a negative A12, A21 plus A11, A22, which we could turn around. So this becomes negative of A11, A22 minus A12, A21. So what basically happens here is that when we switch two rows, the determinant becomes the negative of the original determinant of the matrix. So let us contextualize this. If matrix B is obtained by switching two rows in matrix A, then of course the determinant of matrix B would be equal to the negative determinant of matrix A. We're now going to look at what happens to the determinant if we interchange two columns. So let us say that column 1 goes to column 2 and column 2 goes to column 1. And the matrix that is obtained in this scenario is matrix B. So matrix B would be equal to A12, A22, A11, A21. So once again, we use the shortcut. The determinant of B equal. We take the product of the leading diagonal, which is going to be A12 times A21 minus A11 times A22. Now to compare this to the determinant of A, I would probably need to factor out the minus sign here. So I'm going to have the determinant of b equal negative. So we're going to have a negative a1, 2, a2, 1 plus a1, 1, a2, 2. Because addition is commutative, I can turn that around. So I'm going to have the determinant of b equal the negative of a1, 1, a2, 2 minus a1, 2, a2, 1. And of course, the bracket here actually represents the determinant of a. So the determinant of b is equal to the negative determinant of a. So if we interchange two rows or we interchange two columns, the determinant becomes the negative of the original determinant. In other words, the determinant of b when we interchange two rows or when we interchange two columns is equal to the negative determinant of a. Now, what would happen if we were to multiply a particular row by a constant? So let us say we wanted to multiply, take a constant mu. So row 1 becomes row 1 times mu, or mu times row 1. So let us say that matrix B is obtained as follows. So B would be equal to mu A11, mu A12. We're going to put back row 2, A21, and A22. So matrix B is obtained as follows by just multiplying a single row by a constant mu. The determinant of B, once again, is the product of the leading diagonal, which is going to be mu A11, A22 minus mu A12 times A21. Now, what we realize here is that mu is common, so we can factor that out. So we're going to end up with A11, A22 minus A12 times A21. And inside the bracket here, we actually have the determinant of A. So the determinant of B is equal to mu times the determinant of A. So if we multiply a single row by mu, then the new determinant is simply going to be mu times the original determinant of A. Now, while we can explore the property, we can deduce that a similar thing would happen if we were to multiply a single column by mu. Now, you can explore this property for yourself, but if we were to, for instance, say that B is obtained by saying mu times row 1 and mu times row 2, so if row 1 becomes row 1 times mu and row 2 becomes row 2 times mu, then what would actually happen is that you will end up with mu square times the determinant of A. So if A was a 3 by 3 matrix, all right, a similar thing would happen. If you multiply row 1 by mu, it would be mu times the determinant of the original matrix A. But what if you multiply all 3 rows by mu? What is going to happen is that you're going to end up with mu cube, because there are 3 rows, mu cube times the determinant of A. And of course, you can explore that for yourself.